The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
There. Okay. So let me review a lot of where we've been. We got a secular equation, and the secular equation said, okay, we have this GF matrix and we want a transformation that diagonalizes it. And since this is not a symmetric matrix, this is not a unitary transformation, it's a similarity transformation. We need to find the matrix which diagonalizes this, and it's not going to be one where L dagger is equal to L inverse. Okay, so this is the condition, but we also wanted to be sure that L, that we have a representation, the Q representation, which is has no cross terms, or everything is separable. So 2T was the product of the mass-weighted velocities, and the transformation to the internal coordinate velocities is given by and we chose to define this as the inverse of the G matrix, and so that's just a definition. And then we defined the transformation that takes you from S to Q, the normal coordinates, as L. And so we want to be sure that that L is the same L as we have here. And so now we have Q L dagger G minus 1 L Q dot. Okay, and so from this we get a requirement, well, and we want 2T to be equal to Q. So that requires this L dagger G minus 1 L to be equal to 1, the unit matrix. So that's one. So this is the secular equation. This is a consequence of requiring L to be the transformation from the internal coordinates to the normal coordinates. And the third point of concern is we wanted the potential energy also to be expressed in separable form. And we defined the potential energy, or we defined the F matrix to have this form. And again, we use the transformation now from S to Q, and so we have L dagger F L Q. And we want 2V to have the form Q lambda Q. And so that requires that lambda equal L dagger FL. So this is the solution of the secular equation. These are the two consequences of defining the normal coordinates in terms of the internal coordinates. So we manipulate those. And we showed that this and this are consistent with that, or all three of these things are internally consistent. So we're happy, and we then move on. Okay, so then we began dealing with the vector method. And the purpose of that is to actually work out what the internal displacements are, impose constraints, and work out what the G matrix is. And so up until this point, we're just dealing with formal stuff. And now we're going to begin to actually derive the results that enable us to do calculations. So we define, we write the internal displacements, ST, as a sum over atoms of little st alpha, rho alpha. So we want to find these special vectors which enable us to take an arbitrary displacement and relate it to how that affects the internal displacement. And we say that St alpha is a vector that points in direction of maximum increase in ST. And the magnitude, ST alpha, has a magnitude equal to the change in ST that results when we make a unit displacement of atom A in the optimum direction. So these are vectors that tell the effectiveness of displacements. If we choose displacement of unity in the optimum direction, we get the magnitude of ST. And so this definition provides us with the ability to impose constraints and to derive neat stuff. Okay. So we're going to show how to impose constraints. We're going to discuss the Eckart condition, and we're going to derive this result that G, the matrix elements of G, are given in terms of the masses and St alpha dot St prime alpha. And this is where we really start to make money, because once we can figure out how to define these subject to the constraints that there's no overall translation of the molecule and no rotation, then we can set up the matrix and we're off to the races. Okay, so let me try to show how we do this. Okay, here we again write the definition. And now we want to consider the constraint that there is no overall translation of the molecule. So we would represent rigid translation of the molecule as this vector 1, vector 2, all equal to the same vector. So if all of the atoms are translated the same amount in the same direction, that's the rigid translation. And that's something we want to have zero projection on this. We want to define internal displacements where there is no overall displacement. So immediately we can write ST for this displacement to be equal to epsilon vector dotted into the sum over alpha of the ST alphas. And we want a rigid translation to have no projection on this. So that gives us the first condition. The sum over alpha of little ST alpha is going to be equal to 0. That's wonderful. And that's a vector equation, so it's really 3 equations. So if we talk about motions, I mean, suppose we have a molecule and we're interested in a valence angle stretch, then this sum is going to be, so the STs that would go into the valence stretch would be only the ST for atom 1 and atom 2. So this is an equation then that controls only two, that expresses only 2 of these things, and it's a wonderful way of imposing constraints. If, on the other hand, we have, you know, something like this, 1, 2, 3, a bend, we would like to be able to constrain the molecule, build a internal displacement for the bend where atoms 1, 2, and 3 don't have an overall displacement. And so it's now only 3 of these things. So we might have a huge molecule. But by focusing on internal displacements that are stretches, bond stretches, bends, or torsions, which is pretty much everything, one has constraints of 2, 3, or 4 of these things. And we also know, you know, how to build them, because we know that we want to build the internal coordinate displacements that we want to choose the ST alphas that give the maximum change in the internal coordinate we care about. So the first constraint equation is this one, and it's wonderful. Rotation is trickier. And it's actually a very subtle point, because how do we decide for a polyatomic molecule what's a vibration and what's a rotation? We have to make, I mean, there's, both of these come, you know, when we solve the Schrödinger equation, we clamp the nuclei. And we define a potential energy surface. And then we try to describe what's going to be the motion on this surface. And we'd like to be able to have a separation between vibration and rotation, which is analogous to what we had for diatomic molecules, where there's no ambiguity at all. But for a polyatomic molecule, what is a rotation is not a trivial thing. You have to make a definition. The definition, it's, as long as we're dealing with infinitesimal motions, it's not a big deal. It's not complicated. But if one has very large amplitude motions, like this, how do we decide how to keep the molecule fixed axis? How do we define a molecule fixed axis system in which rotation is minimized? It would be a tempting thing to say, okay, we have a convenient criterion for the principal axis system. The moment of inertia tensor is diagonal. And so we could imagine, even for a large amplitude motion, defining the body fixed coordinate system instantaneously at every point in the motion, so that the inertial tensor is diagonal. This is mathematically simple enough to do, and that would be a unique way of defining rotation. But the problem would be then the inertial, the body fixed axis system would be rotating in an oscillatory way at vibrational frequencies. And that results in Coriolis and centrifugal forces on the atoms, which are very large and would result in enormous problems in trying to describe the energy levels with an effective Hamiltonian. So we don't do that. We have a different way of defining what we mean by the body fixed coordinate system. And it's one where we use what's called the Eckhart condition. And I don't really understand the Eckhart condition as well as I'd like to, because generally we always talk about small amplitudes. And for small amplitudes, it's always possible to make an approximation, which is that the instantaneous positions of the atoms are essentially the same as the equilibrium positions. But the whole point is, what do we really choose? So, but anyway, the Eckhart condition is one where we minimize the non-inertial effects of large amplitude motions. And where do I write this down? Okay, so when the molecule is moving, it's really complicated to talk about what is the body fixed coordinate system. But it's never complicated to say, okay, at some time we had the molecule fixed in space, and so we have the coordinates at equilibrium of each of the atoms in the laboratory frame, and that's going to be our point of reference. So we know at equilibrium we have the set of laboratory coordinates relative to the center of mass. And now let's talk about so here we have the center of mass, and here we have atom 1 and or atom alpha, and here's a motion perpendicular. So this is a rotation. So ST alpha is in that direction, and this is our alpha equilibrium. And so we want to describe rotations, and first we want to define what a rotation would be, and then we want to impose a constraint that says, okay, we're not going to rotate. So and this is really hard, and I'm sorry if I'm a little less in control than usual, because every time I do this I have to learn this, and I hope I'm helping a little bit. So we would like to write what the displacement is that corresponds to a rotation by d omega alpha. So here we have a displacement in this plane. There is a rotation perpendicular, rotation about an axis perpendicular to that plane. This is the thing that we're describing, and that is then our alpha equilibrium plus ST alpha. So this is the displacement, the rotation that we want to make go away. And so we define that R alpha E cross ST alpha is equal to 0. That's the Eckhart condition. So if we choose our, well, that's the constraint. So, okay. So now we'll move on to the G matrix. We want to be able to find a way of expressing the G matrix in terms of things that we can figure out. And we recall that we could write the G matrix, well, we defined the G matrix as D dagger. And we could also write the G matrix as B M minus 1 B dagger. And D was B M minus 1. So this means G T T prime is going to be a sum B T I M minus 1 I B I dagger T prime, and that's the same thing as B T prime I star, but it's real, so we have this. So this is what an element of the G matrix would be in terms of the masses, which we know, and the B's, which we need to know. Okay, but we also had B psi is equal to S. So this transformation tells us how the Cartesian displacements are related to the internal coordinate displacements. We're building up a method of calculating the internal coordinate displacements in terms of the ST alphas. And so if this is true, well then sum over I of B T I psi I is ST. Now this looks like a power series expansion, the first term in the power series. Remember, if the zero these are displacements, so we don't have a zero term. The first term is just a derivative times the displacement. And so we realize that BTI is just the partial of ST with respect to psi I. But we also had the definitions of ST alpha. ST alpha was the gradient of ST, partial of ST d psi alpha x, x plus those three terms. So we have the same symbols appearing here and here. And so it is a straightforward matter to show that ST alpha dotted ST prime alpha is just BTI B T prime I. And so we're going to be able to take these two things that appear here and use that to write G as T prime is equal to sum alpha 1 to n of 1 over m alpha ST alpha dot ST prime alpha. So this is a really important result, that if we can work out the S's, we can work out the G's. Yes?
Can I just back up and ask you a question about the Eckhart?
Yes.
So that equation says that for every internal coordinate, cumulatively all of the interactions between the individual atomic displacements and the the rotation axis has to be 0.
That's right. We can have bends, but we have to arrange for the bends to be such that it's not like this.
Right. But that means for every mode, you have that condition. It's not a cumulative condition for all of the modes.
So you choose, let's say we're talking about, when you say mode, I want to be careful.
Sure.
For every internal coordinate. But we're only interested in the specific classes of internal coordinates.
Right.
Stretches, single bond stretches, and bends and torsions.
But this condition is enforced for each one independently,
Yes.
not for all of them as a whole.
That's correct.
Okay.
So for every internal displacement that we're considering, and that...
Each one has its own Eckhart condition.
That's right. And so, and the Eckhart condition then imposes constraints on either 2, 3, or 4 atoms. And so, it's a little bit counterintuitive because you have a big molecule and you're doing stuff. And you're moving individual atoms and you're not asking anything about what is the result of changing. I mean,
you're going to move the center of mass.
But what I'm getting at is, suppose we're considering atoms 1 and 2, and we move this. We're not interested in how does that bond, the change of the other bond, how is that affected? That comes in later. That we have the F matrix, which is expressed in terms of derivatives of the potential with respect to the internal coordinates. But we have a little bit of vector analysis where we're trying to determine what the mass and geometry contributions are. And so it's 2 separate ledgers that we're playing with.
But that example that you brought up is exactly why I asked. Right? In other words, if you move atoms 1 and 2, you're going to move the center of mass. And that is part of the Eckhart condition for some other internal coordinate somewhere else in the molecule. So is moving the center of mass by changing internal coordinate that affects atoms 1 and 2 not going to violate the Eckhart conditions for atoms 3 and 4, even though the Eckhart condition is only enforced separately for each of the individual modes and not collectively for the molecule?
I think the answer is yes. But I have to admit that this is as soon as I hear the words Eckhart condition, I admit that it's beyond me. I really, I say, yes, I can talk about it, but in terms of imposing the condition, I'm not so happy about that. But, these constraints in terms of the internal coordinates here, these are displacements of atoms. There's no mass weighting here. And so we're requiring that we displace without rigid translation.
The definitions of these R alpha E's, that depends on the position of the center of mass.
Right. So what it's saying is that every internal coordinate that we define involves no rotation of the participating atoms relative to the center of mass. So we're making displacements of the atoms that we've specified in the internal coordinate. And so their contribution to the location of the center of mass and the axis system, there's no translation of those atoms. There's no rotation of those atoms. And it's neat because there's no masses involved. It's just displacements, and so it's a few atoms and it's vector analysis. And then we bring the masses in when we talk about the G matrix. And so I mean, you've got to admire this analysis, but I must say that it's not something that I have internalized. And you guys are going to have to internalize it if you're ever going to do anything with large motions in molecules. Okay, so we have now obtained the equation that enables us to write down the G matrix. And so now we have to actually begin doing stuff. So let's look at the various examples of the kinds of internal coordinates. We have to solve the problem once for each class of internal coordinates. So let's start with the easiest one. We have an internal coordinate that's a stretch. So atom 1, atom 2, and we know just by looking at this picture that the ST1 and ST2 are going to be in the direction parallel to the bond. The STs are the motions that increase the internal coordinate by the maximum amount. And so ST1 is like that, ST2 is like that. And the magnitude of this is also is related to a unit displacement in that optimum direction, which means that these are going to be simply related to the unit vector. Okay, so we know that ST1 magnitude is 1, ST2 magnitude is also 1, because we always we say, okay, we're going to take displacement of the atom in the optimum direction, and by unity, if rho 1 has magnitude 1 and it's in the optimum direction, then ST1 is going to be just 1. Okay, and so then the vector ST1, that is a vector pointing this direction, and so that would be unit vector E21. And that's equal to minus the unit vector 1, 2. And ST2 is, that's a unit vector E12 or minus E21. Okay. So ST for the set of displacements that corresponds to a valence bond stretch is just going to be equal to E21 dotted into rho 1 minus rho 2. This is a displacement of atom 1 by unity to the left. This is displacement of atom 2 by unity to the right. And so that's how we define an internal coordinate. And now we have to ask, are the constraints satisfied? So ST alpha, sum over alpha, has to be equal to 0. And you can see that it's going to be satisfied because they're defined, the two STs are defined as minus each other. So that's certainly true. And then there's the question of the rotation. This is harder. So let's draw, so this is the center of mass. Here's 1, here's 2. And so this is R1E. This is R2E. And this is R12E. Okay. So R12E is just by vector analysis R2E minus R1. Okay, so, but now, yes?
You drew the center of mass somewhere else because this bond stretch could be happening in a larger molecule?
Yes, yes.
Okay.
So, I mean, you always want to define the center of mass somewhere other than the two particles that you're dealing with. Okay, I mean, it could be here,
Right.
but okay. So now, this thing is in a direction parallel to E12. And so we want to have no rotation, and so R12 cross E12 has to be equal to 0. Okay, so what did why did I write all this stuff on the board? The constraint equation is 0 has to be equal to the sum over alpha of R alpha E dot ST alpha. And so we know that ST alpha is either minus E12 or plus E12 for depending on which, and so you end up getting that that this quantity is equal to R2E minus R1E cross E12. Okay, so that's the reason. The constraint equation was reduced to this, and so we have a unit vector in the 1, 2 direction. We have a difference in the two coordinates of the two, and that's also parallel to E12. A vector product of two things parallel to each other is 0. And so this imposition, this choice of these things in this way satisfies the two constraints. Okay, now let's try to deal with the nightmare, which is angled bends. So now we have 3 atoms. And so here is an angle phi. And we want to choose our displacement vectors in a way that, that maximize the change in phi. And so clearly, one of them is like this, and one of them is like this, and one of them is somewhere like that. Okay, so let's call this 1, 3, and 2. So this is ST1, ST2, and that one is ST3. Okay, so when we go a unit displacement in this direction, we can, and this is R31, this is R32. We can calculate how does this increase. So this is delta phi, or it's delta phi for this contribution. And so tangent of delta phi is equal to, so that's that angle, and so that's going to be 1 over R31. But this is small displacement, so delta phi is equal to 1 over R31. Looking at my notes, did I do that right? Well, not quite right. This should have been the magnitude of ST1. Okay, and so now we have, we've chosen the optimum direction. We have a relationship that says, okay, this unit vector, this displacement in the optimum direction changes the bend angle by that much. And now we have to figure out, well, what is this? This is a vector. We have to find out where it's pointing. And so how do we do that? Okay, so if we want a vector pointing in that direction, ST1, we use, okay, so we have a vector here, a unit vector pointing along here, and we have this, we want a vector which is in the plane and perpendicular to this. And so how do we get the plane of the molecule? Well, or something that's perpendicular to the plane. Well, we do E31 cross E32. Okay, that's a vector that's perpendicular to the plane of the molecule. And now we have something that's perpendicular to the plane of the molecule and that is also perpendicular to this direction, and that's this. And so, but now we have to ask, well, what about the magnitude? If we have a cross product of two unit vectors, well, if we have a cross product of two vectors, that's going to be A, B, sine AB. And so we're going to have a sine phi, the equilibrium value here. And so this then provides the direction of this vector. And so this is a vector cross product, and we want to manipulate that into a simpler form, or a form that we're going to use. And so EST is going to be, and this, you just have to do this. E31 dot E32 minus E31 dot E31 E32 over sine phi. So that's just the rules for a vector triple product. And now, what is this? Well, this one is just cosine phi, because it's these two unit vectors. Dot product of two vectors is the magnitudes, both 1 times cosine. And so this is just cosine phi. This is 1. And so we have cos phi minus, I'm missing something. E31 was here. So we have cosine phi E31 minus E32 over sine phi. So we can work out the magnitudes of each of these displacement vectors. These are the easier ones. This is more complicated. But what one does is say, okay, we get these, and we use the constraints to get this one. So you don't do the vector analysis for this. You just say, okay, you define this by satisfying the no translation and no rotation to get this. So that's it. Each of the cases is more complicated, but you can work out then what what these little vectors are, and then you use this equation for working out the G matrix. But now Wilson, Decius, and Cross and Decius have done this all for you. And so you can look in their appendix. And so we're now on page 7 of the notes, and we're also nearly done. You consider, so we want a G matrix. And the G matrix has diagonal and off-diagonal elements. So we have 2 different kinds of internal coordinates. And we could work out all of these S's, but instead, Wilson, Decius, and Cross have done the necessary calculation. So we want this quantity, alpha 1 to n 1 over m alpha s t alpha cross s t prime alpha. We want, that doesn't look right. Is it a cross product?
No.
Okay. And so then there are diagrams in the table, and these diagrams are fantastic. So you have a diagram that looks like this. And so here's 2, and here's 1. And when you have 2 circles around an atom, then that corresponds to a diagonal stretch interaction between, a diagonal element between, for the stretch between 1 and 2. And that's denoted in the table by RR, meaning stretch, and 2, meaning the number of atoms involved and that are common to both T and T prime. And so then you look under that and you get the what this element is. So then there's simple bends, and so here is a diagonal bend-bend interaction. We have one atom. No, that's a stretch. That's an off-diagonal stretch because, so this says we have a stretch, here is a stretch, but one atom in common. That is denoted, and that's not, in the notes it's wrong, G1, R. Right, that's where the prime went. Okay. And then suppose we have a diagram like that. And this would be for a diagonal bend. So we would have G, 3, because there's 3 atoms in common, and phi, implying bend. And so there are diagrams and there are symbols. And you go to the table and you get what you want. But there's also additional notational problems. You find, suppose you have G2RR, the one that you use most. That's written as 1 over m mu. It's mu1 plus mu2. But mu alpha is just 1 over m alpha. So that's notation. You see things like C phi and S phi. Those are obvious. Those are sine and cosine. And what other notations do we get? Okay, and so
the distances are also defined as the inverses.
Right. So the only way to learn how to do this is to actually go through an exam. You owe me a problem, right? There's a problem that was due today. And we need to come up with an example where you will use the notation to set up the G matrix for a problem. And let's just use cis acetylene, which is what is actually this sort of diagrammed in the notes, although there's some problems in the notes. And so cis S1 HCCH. And so I suggest that you set up the G matrix for cis acetylene, and we should stop now.